Nomenclature can be a difficult aspect for students who are first beginning in chemistry. So how do you name these chemicals? What is the basis for how some chemicals are named one way versus another way? So the purpose of this lecture is to try to minimize some of the confusion and to give better clarity on how you name some of these compounds and molecules that you will encounter throughout the entirety of this course. So first of all, we want to discriminate between those types of molecules or compounds that are ionic in nature versus those that are covalent in nature. So you can have an ionic compound or you can have a covalent compound. The easiest way to know what is ionic versus what is covalent is looking to see what are the components of the formula you're talking about. What I mean by that is if you have a metal plus a nonmetal, okay, metals are going to be here in the periodic table. Nonmetals are going to be here in the periodic table. We have the metalloids, which are this line that separates the metals versus the nonmetals. But if you have a metal interacting with a nonmetal, then that is an ionic compound. The nature of this interaction is actually an electron transfer. So whether it's one electron or two electrons are going to be transferred. The most common ionic compounds that you will encounter are within group 1. These guys like to be +1 and give off an electron in order to become +1. Group 2 like to be +2, so they like to give off 2 electrons to become +2. So group 1 and 2, 1A or 2A, like to react with group 6A or 7A, or group 16 and 17. So group 6A usually like to be -2. That's how they achieve their nearest noble gas configuration, so they will gain 2 electrons. And then the halogens like to be -1, so they will gain an electron to obtain their nearest noble gas configuration. So ionic compounds are going to be group 1 and group 2, really reacting with group 16 and 17. Covalent compounds is going to be a nonmetal with a nonmetal. And this is electron sharing, so that's where you get your single bond, double bonds, triple bonds. And so this is an actual interaction between a nonmetal and a nonmetal. And it kind of makes sense if you think about it. You know, carbon dioxide, that's a shared bond between carbon and oxygen. Carbon is a nonmetal, oxygen is a nonmetal. So carbon is going to share its electrons with oxygen. This has a structure that looks like this, C double bond O and C double bond O. This oxygen has 2 electrons here. That bottom oxygen has 2 lone pairs. This is stuff that we'll actually talk about later on, towards the end of the course actually. This has a naming procedure that's a little bit different than this naming procedure, because we're really talking about nomenclature here. So you want to name these in a different set of rules versus these. So covalents really rely upon prefixes, and ionic compounds do not rely on prefixes. Okay, so they really have suffixes. Now these also have suffixes, but these rely mostly on suffixes. So when I say suffixes, you know, your ide, oxide, fluoride, sodium chloride, sodium fluoride, magnesium hydroxide. Here you're going to have a nonmetal with a nonmetal, prefixes and suffixes. So this would be carbon dioxide. You notice I have the prefix di. Actually it's monocarbon dioxide, but we get rid of the mono. So another example here, P2O5. You know phosphorus is a nonmetal. Oxygen is also a nonmetal. So how do you name this? Okay, 2 is di. 5 is penta, so it'll be diphosphorus pentaoxide, okay, oxide. So the prefixes and the suffixes are going to go with covalent compounds and ionic compounds. Just really rely on that last ide. In some cases, we will have a different suffix known as ate. Sometimes we'll see ic as well. So that's a source of confusion as well. Now, another thing that you have to worry about, which makes things more complicated, are polyatomic ions. And these are just things that you just have to memorize. Polyatomic ions are part of your flashcards. So an example of polyatomic ion would be the hydroxide ion. Oxygen is a nonmetal, hydrogen is a nonmetal. These actually have a covalent interaction. O has a covalent bond with H, and here we have 3 lone pairs of oxygen. The minus sign actually goes on the oxygen. This is material that we're going to be talking about, like I said before, in chapter 10, towards the last couple of weeks of the course. These are called Lewis structures, or Lewis. So polyatomic ions have a Lewis structure. You have a covalent bond, but you also have a charge associated with it. Here's another polyatomic ion here, ClO4 minus. So this is called the perchlorate ion. Notice that I'm using the word ion here in nomenclature, so you're going to have to write ion as well, because this is an ion that has a minus charge. This is an ion that has a minus charge as well. The minus charge is really with this whole unit, even though in Lewis structures the minus formal charge, which we'll talk about again much later on in the course, the formal charge from that minus in the hydroxide ion really belongs to the oxygen. Oxygen is an electronegative element. Big thing here, this minus charge technically is with this whole unit, ClO4, but if you're talking about formal charges, the formal charge is shared between these 4 oxygens. So this has a Lewis structure here. It's a little bit more complicated than the hydroxide ion. So I'll just draw it, realizing that you won't see this till much later in the course. This is not the Lewis structure, but the right Lewis structure, because this has a complete charge of minus 4, we want a charge of minus 1, so this pair of electrons will go here, this pair of electrons will go here, this pair of electrons will go here. And really the structure of ClO4 minus is going to look like this, and that minus charge is going to be on this leftmost oxygen. However, that minus charge could also be on the top oxygen. That minus formal charge could be on the rightmost oxygen, and that minus formal charge could be on the bottom oxygen. So perchlorate ion has what's called a resonance, and this is stuff that you're going to be learning in chapter 9, actually mostly chapter 10 is the last part of the course. But it's very important that you know not the Lewis structures for now, because we're talking about nomenclature. It's very important that you know polyatomic ions. So nonmetal with a nonmetal, but the whole thing has a charge. Nonmetal with a nonmetal, the whole thing has a charge. Okay, you can also have plus charges. So NH4 plus, ammonium ion. And you could also have metals involved. Okay, so this is called the permanganate ion, MnO4 minus. That's the permanganate ion. So now the question is, well, how do I name these polyatomic ions? Unfortunately, you're just going to have to memorize these. You just have to memorize polyatomic ions, because they are their own independent unit. They are their own independent group. All right. So juggle here. First, you have to recognize whether the formula that you have to name is ionic or if it's covalent. And then you have to see in your formula the recognition of any polyatomic ions. So some polyatomic ions are easily recognizable, such as the ammonium ion or the hydroxide ion, and some polyatomic ions, such as the permanganate ion, just require straight up memorization. Also the perchlorate ion. Also realize that these polyatomic ions can have metals interacting with a nonmetal, or a nonmetal interacting with a nonmetal. A nonmetal with a nonmetal, you know, is a covalent bond. A metal with a nonmetal, okay, is an ionic bond, but here we also see it behaving as a polyatomic ion as well. So memorize those flashcards, and that will ease naming some of these compounds. There's also substances known as acids. So acids actually can give off a proton. Okay, so here a proton will be designated as H+, and this proton can come on some of these ions, or if they come off. So acids really like to give off protons, so they emit H+, and you may recognize that bases are counter to that. So bases will actually obtain or gather these protons. So how would you name acids? Well, first of all, you have to know their conjugates. Because this H+, this proton, can come off or on, you name them dependent upon the type of counter ion or conjugate that occurs when the proton comes off. So what do I mean by that? Well, there's, again, rules that you have to just familiarize yourself with, and it's not straightforward. They just take some practice and some memorization. So in this case, these ions, they're just halogens actually. They by themselves are called ide. So that means that this would be iodide. If I name this would be iodide ion. Notice that I put the ion term here. This would be the fluoride ion. What would this be? This would be the chloride ion, and this would be the bromide ion. Ide, and ide. When you make it into an acid form, then you have Hi, because H plus will neutralize I minus to give you Hi. Here you have HF. Here you have HCl. Here you have HBr. So the H's imply that it's an acid. That H can actually dissociate, the proton can come off, and really strong acids will just give off that proton. Actually, what you see here are 4 very strong acids. But how do you name this? So ide in the anion form, once it picks up a proton, it becomes ik in the acid form. This is this new suffix. So that means Hi becomes hydroiodic acid. HF becomes hydrofluoric acid. Everyone knows HCl is hydrochloric acid. And HBr is hydrobromic acid. So we have the ik, and then we also have the hydro prefix. So ide in the anion form, add an H+, you have hydro plus ik. Hydro is the prefix, ik becomes the suffix. With really the halogens that we see this phenomenon. What about the oxo acids? So these actually emit H+. All acids are going to emit protons. You might as well just know that now, and all bases are going to take those protons. That's acid-base chemistry. But these oxo acids can emit hydrogen ion, but they also have oxygen in the polyatomic ion form. So how will you name these? Well, if you go back to your flashcards, your polyatomic ions, these have the suffix of 8. So that means this will be nitrate. Let me write that down. Nitrate ion. I don't want to forget that ion at the end because these are ions. Here we have the sulfate ion. We have the carbonate ion. We have the phosphate ion. And then here we have the perchlorate ion. So nitrate ion, sulfate ion, carbonate ion, phosphate ion, and perchlorate ion. You just have to memorize these as part of your flashcards. What happens when you add a hydrogen ion to this? The H plus will neutralize the minus in NO3 minus, and you have HNO3. Here you have H2SO4. Remember the switcheroo that occurs involves charges. Same thing here, H2CO3 would be H3PO4, and this is just HClO4. So anytime you have 2 charges that are going to interact with one another, as in an ionic compound, you want to do the switcheroo. You switch the charges. How will you name these? So Ite is the anion form, and then you don't add the hydro like you do here. What happens is that the end becomes just ic. So HNO3 becomes nitric acid. H2SO4 becomes sulfuric acid. H2CO3 becomes carbonic acid. H3PO4 becomes phosphoric acid. And finally, ClO4 minus, the perchlorate ion, becomes perchloric acid. So it may help if you recognize the conjugate base versus the acid. Nitrate becomes nitric acid once it gets the proton. Sulfate ion becomes sulfuric acid when it picks up the proton. It actually picks up 2 protons because of the ionic nature, the switcheroo. Same thing with carbonate ion. Carbonate picks up 2 protons and becomes carbonic acid. Phosphate picks up 3 protons. We call this triprotic, just as we will call these previous 2 diprotic. So this can actually give off 3 protons. Acids give off protons. So it's phosphoric acid because the counter ion is named the phosphate ion. And this is the perchlorate ion. It picks up a proton, 1 proton, and becomes perchloric acid. So here we have the ic term. Here halogens, when they pick up the proton, become hydro plus ic. So prefix plus suffix. Here we just add the suffix. Okay, so these oxo acids can also come in varying forms of oxygen. So these are also polyatomic ions, just as these are. These will have a covalent structure. These will have a covalent structure independent of them picking up that proton. It's very important. It's independent of them picking up that proton. So how will we name these oxo acids that have less amounts of oxygen in their covalent structure? So in this case, sulfite ion is just something you have to memorize. We can also put another one here. 1 less oxygen in nitrate becomes nitrite. So we can also name that here. So polyatomic ions, our flashcards tell us that nitrate, NO3 minus, and then we have nitrite. We have sulfite ion. We have nitrite ion. It's actually repeated from this, so I'll omit that. Here we have phosphite ion. And here we have what's called the hypochlorite ion. What happens if we add the proton to this? If we add the proton, this becomes HSO3 minus, becomes HNO2, becomes H3PO3. Okay, remember when we add the H plus, we do the switcheroo, and this becomes HClO. Okay, HClO is different than HClO4. How will we name these particular types of oxo acids that have a smaller number of oxygen in their covalent structure, in their sharing of electrons, that structure? So again, look at the suffix here, nitrite, sulfite, phosphite, chlorite. So in this case, all of these have ite, and the acid form is going to change to us, O-U-S, as a suffix. So HSO3 minus is going to be sulfurous acid. HNO2, 1 oxygen less. Nitrate, 1 oxygen less is nitrite. The acid form is going to be nitrous acid. Phite is 1 oxygen less than phosphate. The acid form is going to be phosphorus acid. HClO actually is a conjugate of ClO minus and it's hypochlorite. Ite becomes is after it picks up the proton, and it's hypochlorous acid. It's important to recognize that this H plus can dissociate. The strength of an acid or how good an acid is depends on how well it could give off that proton. These strong acids here really like to give off that proton. In fact, HCl, if you ever have or hold a bottle of HCl that's very concentrated, it's 100% essentially H plus and 100% Cl minus. So, there are some polyatomic ions that have differing degree of oxygens. They're still oxo acids, but they have different amounts of oxygen. You notice here you have ClO4 minus. Here you have ClO minus. So it's still a minus charge, and this is still a covalent compound. In fact, I drew the structure ClO4 minus here. Okay, so this is the structure of ClO4 minus, where that minus on the ClO4 minus can be shared between this oxygen, this oxygen, this oxygen, and this oxygen. That's resonance. But you also have the ClO minus form. That is Cl covalently bonded with one oxygen, and that whole thing has a minus charge. So if I were to draw the Lewis structure of that, it's going to look like this. Okay, so notice you have a bond between the Cl and the oxygen. Oxygen has 3 lone pairs of an electron. This whole unit has a charge of -1, even though formal charge tells us that the minus charge in this ion is really localized to the oxygen. Again, this is chapter 10 material, not stuff for you to know now because we're talking about nomenclature. I just want you to realize that this is a covalent compound, but within that covalent compound, the whole thing has a minus charge, so it is a polyatomic ion. So this chlorine and oxygen, the chloro-oxo acids, are a little bit tricky because they have different levels of oxygen. So you can have ClO minus, you can have ClO2 minus, ClO3 minus, ClO4 minus, and all those forms can pick up a proton, become the corresponding acids. So here they pick up the proton and become an acids. Acids usually give off protons, and they can be the conjugate base. So depending on how strong these acids are, it will tell you how well they can give off that proton. If it's a weak acid, the proton tends to just stay. So that H plus is what we know as dissociable, and acids are measured by how dissociable that H is. It can come on or off. Really good acids, it will come off. How do we name these? So this and the hypochlorite ion, when it picks up a proton, it goes to S, so this is hypochlorous acid. Polyatomic ion with the least amount of oxygen is hypo, and this polyatomic ion with the most amount of oxygen is per. So this would be the perchlorate ion. It goes to ic, so when it picks up that proton, it becomes perchloric acid. So if you have 2 oxygens, that is just a chlorite ion, and when it picks up that proton, it becomes chlorous acid. ClO3 minus is the chlorate ion. Picks up that proton, 8 goes to ic, it becomes chloric acid. Notice that I use chlorine, but I could replace this with any other halogen. So for example, instead of chlorine, if I used bromine, this would be hypobromous acid. This would be bromous acid. This would be bromic acid. This would be perbromic acid. Right? So I could also use iodine, the other type of halogen. That would be hypoiodous acid, HIO. HIO2, iodous acid. HIO3, iodic acid. HIO4, periodic acid. So bromine, iodine, chlorine, the halogens, let's just do one more. Fluorine. All right, instead of Cl, if I had fluorine here, this would be hypofluorous acid, or the fluorite ion. This would be fluorous acid, or the fluorite ion. This would be fluoric acid, or the fluorate ion. This would be perfluoric acid with the perfluorate ion. I'm just replacing the Cl with a different type of halogen. Talk about ionic compounds, we have to include the special case for what are known as the D block elements. The D block elements are right here, this rectangle that goes from group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Group 3 to group 12 are your transition metals. So I'll highlight these. The stock system. Rectangle here are known as the D block elements, and you're going to have to use Roman numerals to elucidate its charge. I'm not going to get into the stock system, but these are given by Roman numerals because sometimes these transition metals can have more than one charge. So for example, iron can be in an iron plus 2 form, or it can be in the iron plus 3 form. Okay, something like vanadium can be in the plus 5 form. It could even be up to the plus 3 form. So some of these can go very, very high in their oxidation number, or very, very high in the amount of electrons that they can give off. These are going to be positively charged, but they can vary. The reason why is the D block elements, the D electron shell can hold and accommodate a lot of electrons, and those electrons are free to leave, so you can have multiple charges with the D block elements. So just be aware that you have to go over some practice problems that will help you familiarize and get more comfortable with this concept of nomenclature. So first one here is sodium chloride. You have to ask yourself, is that an ionic compound or is that a compound? Well, we have a metal in sodium, we have a non-metal in chlorine. Na likes to be +1, Cl likes to be -1. The correct nomenclature for this would be an ionic compound. That's how it's formed, but it's called sodium chloride. No prefixes because it's a metal, non-metal. Same thing here. This is going to be silver, which is +1. NO3 is a polyatomic ion that goes NO3-. And silver is part of this rectangle of transition metals where we have to designate the charge. And how will we designate it? We will designate it with Roman numerals because silver is right here in that D block element. And silver is going to have a +1 charge here with nitrate, and this is going to be silver 1 nitrate. The silver +1 charge is designated by a Roman numeral. I see a lot of students put Roman numerals where they shouldn't, and a lot of students put a Roman numeral where they should not have a Roman numeral, but they also don't put the Roman numeral where they should have put the Roman numeral. All right, so it's worth noting, how ionic compounds form. You have to look at switcheroo here. All ionic compounds are going to be that switcheroo. And when you look at a problem like this and determining whether it's an ionic compound or covalent compound, you're going to have to reverse engineer it, particularly if you're looking at metal with a non-metal. So what about this? Is this covalent or ionic? Barium, and we know barium is a metal and it likes to be +2. This is a polyatomic ion, chromate. You just have to memorize that. So this actually is an ionic compound. The answer is barium chromate. Barium is not part of our transition metal block. Barium is right here. Group 2 likes to be +2. Okay, you may be wondering, look at that chromate, CrO4-2. That's a non-metal, and that's a non-metal, so that's a covalent compound. You're right, chromium is a covalent compound, but the whole thing is a -2 charge. This is a polyatomic ion. So you can have a polyatomic ion form an ionic compound with a metal that has its own charge, plus charge. Same thing here. Calcium likes to be +2. Hydroxide ion is OH-. And if you can look at your flashcards, you'll realize this is the hydroxide ion, a polyatomic ion. This is called calcium hydroxide. To put Roman numerals, because there's no transition metal here. This one you will. Zinc is a transition metal. And zinc, CO3 is the carbonate ion. It likes to be +2. So how does zinc form with carbonate ion? Look at this formula here, ZnCO3. It's 1 Zn with 1 CO3. So what does this charge have to be to get a 1-to-1? It has to be +2. So when you do the switcheroo, it's going to be zinc CO3 2, but the 2's and 2's cancel each other out. Remember, we want to reduce those numbers. So zinc, this one, sodium is a metal. This is the sulfate ion. Sodium likes to be +1. Sulfate likes to be -2. Let's do the switcheroo. Do with all ionic compounds. Formula is going to be Na2SO4. It's called sodium sulfate. This is Al, likes to be +3. Oxide ion is -2. This is an ionic compound. You don't need Roman numerals because nothing is in our transition metal block. This is called aluminum oxide. E is cadmium. It's a transition metal. So you're going to have to figure out the charge of that cadmium and articulate it using a Roman numeral. Bromine. Bromine likes to be minus. Cd. So what charge will Cd be? Okay, it's the switcheroo, so this is going to be +2. That +2 will go here. That minus will go here. This is cadmium 2 bromide. K is K plus potassium. Nitrite is NO2 minus. This is a polyatomic ion, but that minus sign is in this whole unit. So this is going to be potassium nitrite. Two answers. So iron has a charge. It's a polyatomic ion with nitrate is the polyatomic ion. So this is nitrate. What does iron have to be in order to do the switcheroo? It's going to be +3. Okay, so when +3 goes here, that minus sign goes here. This is iron 3 nitrate. Ask why did I put in Roman numerals? Because iron is part of the D block element. Can exist as +2 or +3. Exists in the +3 form. It's also known as ferric nitrate. Ferric nitrate, we don't have to use the Roman numerals, but I really prefer this nomenclature. Okay, this is old ferric, ferrous is iron +2, but really let's emphasize the Roman numeral system here. NH4, 3PO4 minus, so this NH4 is a unit, has 3 of them. That's a polyatomic ion, that's the ammonium ion. Phosphate is PO4 minus 3, so one polyatomic ion, whole thing is a plus charge. Another polyatomic ion, the whole thing is a -3 charge. This thing is ionic. Even though the individual things are covalent, it's a polyatomic ion interacting with another polyatomic ion. Both those come together to form a ionic compound, and this is going to be called ammonium phosphate. Numerals because there is no transition metal in there. One more here. Calcium is K+. Here's a polyatomic ion. ClO3, it's minus. That's one of those strange oxo acids here. This is actually called the chlorate ion. So this is potassium chlorate. M is Mg+2. Sulfide is S-2. These are magnesium sulfide. Finally, copper is a transition metal. Copper 1. Roman numeral now because look at your periodic table. Where is copper in your periodic table? Copper in your periodic table is right here. Copper 1 and C2O4 minus 2 is the oxalate ion, so this is copper 1 oxalate. You're given the actual name of the chemical and you have to deduce the formula. So let's do that here. Barium chloride. Barium is +2. Chlorine is -1. Chloride. Chlorine is the element. Chloride exists just -1. So the switcheroo, this is BaCl2, ionic compound. Zinc fluoride. There's no Roman numeral here. So F- is the fluoride ion. Zinc is going to be, well, we don't know what charge zinc is going to be in, so I'm just going to assume it's going to be plus, and we'll just call it, well, I'll assume it's +2, so I'll call it ZnF2. On the exam, I would be more explicit and tell you what would be the charge on that zinc. But zinc most likely is a +2 as a transition metal. This is a better example. Lead, notice the Roman numeral 2, so that means Pb +2. What is iodide? Okay, iodide is I minus. Iodide comes from iodine. So iodine is the element, iodide is the ion. Halogens like to be -1. We'll do the switcheroo and you get PbI2. Hydroxide, ammonium is NH4+, polyatomic ion, hydroxide, polyatomic ion, OH minus. This is going to be NH4OH. Potassium chromate. Potassium is +1. Chromate is the formula CrO4 - 2. We do the switcheroo here, and we get K2CrO4. Ionic compound. This is a polyatomic ion. Bismuth 3-chloride. I like this problem here because it tells us bismuth is a transition metal. Bismuth is going to be +3. Chloride is Cl-, so this is going to be BiCl3. Okay, all ionic compounds are doing the switcheroo. Magnesium perchlorate, magnesium is +2. The perchlorate ion is ClO4-. The minus switches with the +2, and you have Mg parentheses ClO4 2. Okay, notice that ClO4, that whole unit, this whole unit picks up that +2 charge. Copper 2 sulfate, +2. Numerals, stock system, transition metal. Sulfate is SO4 - 2. Look at your flashcards, do the switcheroo, and this is going to be CuSO4. Iron 3 chloride, iron is +3, Cl is minus, so this is going to be FeCl3 when you do the switcheroo. Calcium cyanide, calcium is +2. What is Cn? It's Cn minus. This is a polyatomic ion. It's a covalent compound. It's C triple bond N with a negative charge. Again, that's going to be chapter 10 material. But the formula for calcium cyanide is going to be Ca parentheses Cn underscore subscript 2. Because that Cn picks up, that whole unit picks up the +2 charge. Copper 1 sulfide. Copper is +1. Sulfide is -2. CuS2 when you do the switcheroo. Okay, do the switcheroo if you have a covalent, do the switcheroo if you have an ionic compound. Silver carbonate. Silver is Ag+, transition metal, but it's going to be plus. And carbonate is CO3 - 2. This is going to be Ag2CO3. Should put this Roman numeral here, but silver is just exclusively +1. Hypochlorite. What is hypochlorite? Hypochlorite is ClO, cadmium. So what's going to be the charge on cadmium? Cadmium is a polyatomic ion. Usually cadmium has a charge of plus. ClO has a charge of minus. They should put a Roman numeral on this, but it's going to be CdClO. Sodium bicarbonate. Sodium is Na+. Bicarbonate is HCO3-. Okay, flashcards. Do the switcheroo. This is going to be NaHCO3. Aluminum acetate. Aluminum likes to be +3. Acetate, we really didn't talk about acetate, but its formula is this, C2O2. Switcheroo, it's going to be Al parentheses C2H3O2. That whole thing has a 3 charge in it. Phosphate, nickel is a transition metal, +2. Phosphate is PO4 - 3. Do the switcheroo. Sodium sulfite. Sodium is this. Sulfite is SO3 - 2. Switcheroo, it's going to be NO2SO3. Tin 4 oxide. Tin is an element that has the elemental abbreviation SN. It's +4. Oxide is -2. We do the switcheroo. And so ionic compounds do the switcheroo. Covalent compounds, no switcheroo. Prefixes, and the corresponding suffixes. Examples of covalent compounds. Notice here we're not looking at doing any switcheroo, and we're really not focusing on charges because these are bonds that are going to be shared. So how do we name these? These have their own nomenclatures, and the emphasis is on prefixes. Di, tri, penta, etc. Let's try naming some of these. C is a nonmetal, S is a nonmetal. So this would be carbon, right? Because of the two S's. Nonmetal plus nonmetal. Look at the prefix. The prefix for 2 is di. It's not monocarbon disulfide. We omit the mono. Right? So if the leading element is just 1, we don't add the mono. Iodine pentafluoride. That's going to be I is iodine. Penta is 5, so fluoride is actually fluorine. Because of the nomenclature rules, we call it fluoride, and there's 5 of them. Pentafluoride. Nonmetal, nonmetal. Xenon is a nonmetal. Fluoride is a nonmetal. Hexa is 6, so XeF6. This will have its own covalent Lewis structure, so will this. 5. So this will be diphosphorus. So the leading element is not 1 but 2, so that gets diphosphorus pentoxide. Some people actually name this as diphosphorus pentoxide. They remove the A side. I would count either one correct. H2O is going to be dihydrogen oxide. Is on the second element. It's not leading, so you can add the mono to the second element. That means we have 2 hydrogens and 1 oxygen, dihydrogen monoxide. You may know this as its most famous name, water. Okay, that's just water. Dihydrogen monoxide, H2O is water. So you can tell your friends that I'm going to go or I have a bottle of dihydrogen monoxide, and they may freak out or something. CCl4, okay, monocarbon, but we don't add mono because it's the leading element. So 4 is tetra, so this would be carbon tetrachloride. You actually use carbon tetrachloride a lot in organic chemistry. Phosphorus pentafluoride. Phosphorus is a nonmetal. Fluoride is a nonmetal. P, because it's 1 phosphorus. Penta is 5. This is PF5. Okay, PF5, IF5. Sulfur trioxide. Sulfur is S. Tri is 3. It's going to be SO3. Okay, SO3 is different than SO3 minus. Okay, this is the sulfide ion, and this is sulfur trioxide. N2O5 is dinitrogen pentoxide. Non-metal with non-metal. Nitrogen dioxide, NO2. ICL4 minus. So this is an ion. So iodine tetrachloride ion. You add that ion to it because it is an ion. Chlorine trifluoride is this one. Chlorine trifluoride. Carbon tetrabromide. CBr4. And finally, B2F4, it will be diboron tetrafluoride. Now, boron is technically a metalloid, so it's neither here nor there. The nonmetal, F is fluorine, that's a nonmetal. It's going to be diboron tetrafluoride. Diboron tetrafluoride. This my suffixes. Ide. The difference between this and covalent compounds, number 1, no switcheroo, and number 2, the prefixes, mono, di, tri, tetra, penta, hexa. Di, tetra for 4, tri for 3, tetra, di, penta, tetra. All right, so if you see our formula that has phosphorus pentafluoride, that's pretty easy, PF5. But what if you see something like this, okay, N2O5? Are you going to give it this is a polyatomic ion? No. Is it an ionic compound? No. There's no switcheroo, there is no charges, it's not a polyatomic ion, there's no charge involved. This is just straight up N2O5. So really that's the confusion, differentiating a polyatomic ion versus an ionic compound. In this case you have to know what is ionic, and those that are just simply a nonmetal interacting with a nonmetal. So that is nomenclature. We went over several examples and several rules. Practice makes perfect.